Okay, in this video, we're going to take a look at the following examples. We've got researchers and they are trying to estimate the average length of all female Komodo dragons. So that's what's pictured over here is a Komodo dragon. So these are huge lizards, as you can see by their weight. So these lizards, for example, eat things like boar and deer and really large mammals, hopefully not people. But these are really large animals. And so for the Komodo dragon, let's say we go out and we collect a sample of 8 female dragons. And these are their weights in pounds recorded over here. And so what we'd like to do with this relatively small sample of 8 lizards, Komodo dragons, is estimate what is the mean weight of all female Komodo dragons. So in part 1, it's asking us to estimate that with a 95% confidence interval, and in part 2 with a 90% confidence interval. So we've already seen 95% confidence intervals. Let's take a look at that one first. So first we would take our sample of 8 values and calculate the mean. So I would add these all up and divide by 8, and that gives me a mean of 155.5 pounds. Next is we need to know the standard error for the sampling distribution of the mean. So to find that, we would take the standard deviation of the population and divide by the sample size. So sigma is 25. We've got 8 values in our sample. So we're going to take 25 over the square root of 8. And calculating that gives us a standard error of about 8.839. And that's all we need for 95% confidence interval. I need to know what my mean is and what's the variability that I should expect in that estimate. So I've got my lower limit would be going 1.96 times the standard error below my sample mean. So that's our lower limit, and then the upper limit would be our sample mean, which is the 155.5 pounds over here. And we're going to add to that 1.96 times the standard error, which is the 8.839. And calculating the lower limit, the 155 minus 1.96 times 8.839 gives us 138.176 pounds, and the upper limit, computing that, would give us 172.824 pounds. And so I won't write it, but I will say it, and this is important. We want to be sure that we can interpret this properly, as I would say there's a 95% chance the interval from 138.176 pounds to 172.824 pounds contains the mean weight of all female Komodo dragons. So in that explanation, I both attached the uncertainty to my interval and used my interval as a means for estimating the population parameter. Alrighty, so in part B, they're asking us now to give a 90% confidence interval. So we're changing the success rate. And so what's not going to change in this process is we still have the same sample, and our sampling, since our sample is the same size, the standard error of the sampling distribution is going to be the same. But now we're requiring a lower threshold on our interval. So we're saying we want this to be successful just 90% of the time, so a little less than the top one. So what that means is for 90% of the samples that we pick from the sampling distribution, we want this to work. So we want to find out what these cutoffs are over here. So I'm going to call this one, say, minus z alpha over 2, and I'm going to call this cutoff z alpha over 2. And how all this notation relates back to the confidence level, we're going to say here that the confidence level is 90%, 0.9. So this value alpha is the stuff that's not within the middle 90%. So that's the remaining, in this case, 10%. And then we divide that in two because half of the missing 10% is down here and the other half is up here. So these values are no longer going to be 1.96. So I could either use the standard normal distribution table to look up these values, or we can use the qnorm function in R. And so to use the qnorm function, we've got this normal distribution, and so to find z alpha over 2, we could say that the total area to the left of that is the 0.9 plus the 0.05. So we've got 0.9 in the middle, and then we've got 0.05 over here. So adding those two together, this is going to have 95% of the area to the left in this case. So to find this z alpha over 2, I could take q norm of 0.95, and I've got a mean for the standard distribution of 0 and a standard deviation of 1. And so from R, we get an output that's approximately 1.645. So that would be the z alpha over 2 value that we found over here, and this one would be the minus 6.45. So now when we construct our confidence interval, the only thing we're going to need to adjust is how many standard, what multiple we're going to multiply by the standard error. So my lower limit is going to be 155.5 now minus 1.645 times the same standard error for my lower limit, and then for the upper limit we're going to get the 155.5, and then we're going to add to that 1.645 times the standard error, which again is the 8.839. And so calculating those limits, the lower limit comes out to 140.96, and the upper limit comes out to 170.04. And here we're estimating the weight in pounds for female Komodo dragons. We would interpret this as saying that the interval from, say, 141 pounds up to 170 pounds has a 90% chance of containing the population mean weight for all female Komodo dragons. So we adjust now the percentage success that we attach to this interval. Now this is only 90%. And so if we compare these two estimates, the one I got in A and the one that I got in B, you can see that there's a trade-off. So what was good about the answer in A is this had a higher likelihood of being successful, which is good. And here were the endpoints of my interval. And if I compare that to part B, the good thing about this interval is it was a little more specific, right? And what I mean by that is the interval was a little bit more narrow than the one that we got in A. So if I make my interval a little bit more narrow, it gives me a little bit more specific estimate for this population parameter, but the trade-off is the rate of success is less. So that makes sense. If I make if you think about these as like fishing nets that are trying to catch our fish, which is the population parameter, the wider I make my net, the more likely I am to catch the fish in this case. But the problem is when your net is so wide, you're not exactly sure where in that range of values this might fall. So a wide range of values might not be all that desirable because it's not very specific. But the good thing is that it has a really high likelihood of capturing the population parameter.